Oleg, we need to talk.
What about?
Calibration. You and your rhymes and your thermometers.
What about them?
Well, we're not going to be sticking our telescopes into boiling water, are we?
Well, you did talk about antenna temperature earlier.
Yes, but that's much colder. We have cryogenics on them. They're much colder than your freezing water.
Well, it was what we call in the business an imperfect analogy. Like the duck we modeled with a cigar, remember?
That was a dirigible.
Okay, maybe so. Right, let's get serious.
Yes, let's talk about what calibration really looks like in practice.
So let's say we have two dishes here looking up, and they gather signal into receivers, and that is then correlated together. And the signal, of course, travels through an atmosphere of some kind up here. From the rhyme, you know that the measured signal is given by the coherency matrix here. All the intrinsic source properties are in here, including the Fourier transform, times a Jones matrix JP and the Jones matrix JQ conjugate, describing the signal paths of the two antennas.
Up to now, we've been living in an idealized world, but in the real world, we know there is an error in any measurement. So where's the noise?
There is indeed measurement noise, so there's an extra additive noise component here that we actually measure, NPQ. And from the radiometer equation, we know that this component is Gaussian in the real and imaginary parts. So we write it like this. N for normal, with a zero mean and a standard deviation of sigma vis, which is given to us by the radiometer equation. Our science goal is in the x's here, and calibration consists of estimating the unknown j's so we can get at the x's. Remember our ungraduated thermometer. The j's are the markings on the scale.
So what are our reference points? Where do we find freezing and boiling water in interferometry?
Well, what we can do is we can point our antennas to a source whose properties we already know from previous observations, say here in this direction. Such sources are called calibrators. Let's say we observe a point like calibrator at the phase center. We then have this kind of rhyme. VPQ of the calibrator equals Bcal, the brightest matrix of the calibrator, times JP times JQ conjugate, and plus, of course, the noise. Now, we know Bcal from previous observations, and we can measure Vcal for many different combinations of antennas, and therefore we can then solve for JP and JQ, and that gives us our graduated thermometer.
But now we're assuming that the Jones matrix stays relatively unchanged when we look from the calibrator to our target. This will only work if our instrument and the atmosphere remain stable. On the other hand, we know that electronic response eventually drifts, and we know that the atmosphere can't be stable for very long either.
Right, so when observing, we must cycle back and forth between the target and the calibrator, just so we can track this changing response. So over time, your observation looks something like this, with the antennas swinging back and forth between the calibrator and the source. This is what we call the target source. This is time we spend on the target source, and then we go back to the calibrator, etc. This is called the calibrator scan, and this is called the target scan. The relative time you spend on one or the other is called the duty cycle. So we can talk about the target duty cycle or the calibrator duty cycle. Now your underlying J's that you're trying to solve for, they're doing something like this. Then in the calibrator scans, you get a solution for them, like this, and then you interpolate. We do what we call a transfer of these solutions from the calibrator to the source. This sort of procedure is known as first generation calibration or calibrator transfer, because we get solutions for J on the calibrator here and here and here and here, and then we transfer these solutions in between onto the target scan here, here, and here.
So this procedure must be introducing errors. For example, how well do we know the calibrator source model?
Good point. In fact, there are several sources of error in the calibration procedure. Let's sketch them out. You've just mentioned the first one. We'll call that one sigma b, and that's the error in our prior knowledge, or simply how well we know the properties of the calibrator.
And then there's noise in the calibrator measurement, this n here.
Indeed, and noise also introduces an error into the solutions. We'll call it sigma sol. And you can work out, and also intuitively it actually makes sense, that this error goes as the standard deviation of the visibility noise, sigma vis, the one given by the radiometer equation here, over the brightness of the calibrator. This is really just the inverse of the signal to noise ratio, times 1 over the square root of the number of measurements we use, number of times, numbers of frequencies, So that's the number of time and frequency samples in our solution interval. So if you solve for the gain over longer intervals, your solutions are better constrained. Sigma sol goes down.
If you take longer intervals, you no longer track this short-term change in the Jones matrix here.
Indeed, exactly. And that's where the third source of error comes in. Let's call it sigma var. This is the intrinsic variation of J over the solution interval. So kind of the difference between the purple curve here and the green solution. Now, obviously, this error is going to go up with the length of the solution intervals.
And notice that these three errors are inherent to the calibrator scans. We haven't even gotten to the target scans yet. Don't we also make errors when interpolating these solutions?
Indeed, we do. And you can see it here as the difference between the purple curve and the red line. We introduce another error in the interpolation. Let's call it sigma transfer. Now, obviously, this error is going to go up if you make the duty cycle longer. So if our calibrators are further apart. But also, it's going to go up with the angle theta here. And theta is the angle giving us the separation between the source and the calibrator. Because obviously, the further apart the source and the calibrator are, the more they're looking through a different atmosphere, a different signal path.
Right. So I noticed that these four things are all in tension with each other. For example, to minimize these terms, sigma B and sigma sol, we want to use the brightest, most well-measured source in the sky.
Yes, but that might be very far away from our target. So then this error is going to go up. So maybe we have to use a weaker but closer calibrator.
But then we'd need to increase the solution interval to drive this error down.
Okay, but then we don't track the variation so well, and then this error goes up. So, how do we work around all this? Well, we look closer at the structure of the Jones matrices here, and then we devise calibration strategies to exploit them. And don't forget, we can use multiple calibrators, not just one.
In practice, we hardly ever do any of this by hand. People have figured out standard calibration strategies for most reasonable cases. And as an observer, you'd simply use a software package such as CASA to turn the crank and apply these things. But here we're going to peek under a hood just a little, because why not?
Yeah, why not indeed? Let's see what sort of Jones matrices we really need to solve for. We've learned to write pretty complicated rhymes, but for basic calibration, we only need to solve for the dominant effects, which can be quite simple. So we're going to keep it simple, we're going to ignore the exotic stuff.
Yes, like polarization and direction-dependent effects. This leaves three basic things we need to almost always calibrate for. These effects have different signatures, and that is what allows us to distinguish them.
So here's our observation again. Firstly, you have the sensitivity to frequency, what we call the bandpass or the B Jones. Our telescope is not uniformly sensitive across all frequencies. In fact, a receiver works in a certain band of frequencies across here, what we call the pass band, and then the sensitivity looks something like this on amplitude. And there could be wriggles across here for various reasons. So you have this fairly complicated structure and frequency, and it could actually be different across antennas. This is why we write it as BP and BQ, and it's a diagonal matrix, but fortunately it's actually engineered to be fairly constant in time.
So then we need to solve for B with short frequency intervals, as short as one channel even, but then we can use very long time intervals.
Right, and now on top of this you have something we call the flux scale. This is just the overall sensitivity level of the system, kind of like the scale of the thermometer. But you can also think of the flux scale as just this entire bandpass thing, scaling up and down.
Now what about things that change with time?
That's the next one here. We call this the gain or the G Jones. This is our time variable complex gain, or simply we call it gain. It has an amplitude and a phase component. The amplitude part usually comes from the electronics, and this will tend to evolve slowly, or maybe even not at all.
And then maybe we can just absorb it into the flux scale here.
That's right, often we can. But then you also have phase, and this comes from both the electronics and the atmosphere here, so it will probably have a range of behaviors. It's going to have this sort of slow evolution on large scales, and then it's going to have small and fast jitter.
Right. So this we solve on short time scales, but we usually assume it has no structure and frequency. So n nu here is just all the channels.
And then there's a third important effect. We call this delay error, or K Jones. This is anything that causes the signal to incur an extra delay that we haven't accounted for. The troposphere here imposes a delay, and maybe one of the cables here is a little bit longer. And maybe there is a delay in the electronics.
Maybe the geometric model that the correlator uses for fringe stopping is slightly off. So what does the delay do?
Well, delay translates into a phase error, so you can see the Jones matrix looks like this. It's an exponent of I phi, and this phase phi is given by tau over lambda, where lambda is the wavelength and tau is the extra path that the signal had to travel. Or equivalently, you can give it as delta times nu. So nu is frequency and delta is the delay time. So as a function of frequency, your phase looks like a slope.
And if your phase slope is too big, due to the delay error, it can begin to wrap.
Indeed, you might get phase wrapping over your bandwidth from minus pi to pi, and that can really make things interesting. So this Jones term has a function on frequency, but it's a very simple structure because it can be represented by a single number, the slope, or equivalently this delay time.
And now does the delay evolve in time like gain?
Well, it really depends on your regime. So at lower frequencies and with relatively narrow bandwidths, your delay is going to be mostly instrumental and it's going to be slow.
Kind of like the bandpass here.
That's right, exactly. And then at higher frequencies and with wider bandwidths, atmospheric delay is going to become dominant. And that evolves quickly. More like the phase term here, this kind of structure. So we end up with this sort of approximate rhyme. We say that the observed calibrator visibilities are Kp times Bp times Gp times the calibrator brightness times the conjugate. So this is kind of really very simplistic.
Yes, but some terms here capture a mix of instrumentational and atmospheric effects, but in many cases it's a perfectly good approximation.
Right, so now let's put together some calibration strategies. First, I'm going to draw this two-dimensional matrix representing our observation. So time goes this way, frequency goes this way, and then let's say this is the edge of our band on frequency, and our observation starts here, and it ends down here. Now, let's start with bandpass and flux scale. These vary very slowly in time, so we don't need to observe them frequently.
Perhaps just at the beginning of the observation and maybe at the end of the observation here, like this. Now this here is going to represent our solution intervals. Because bandpass has complicated frequency structure, we'll need to solve for it in short frequency intervals like this.
And then this line here represents the bandpass solutions being transferred over the rest of the observation in between here.
So what does this tell us about the bandpass calibrator?
Well, the solution intervals here have to be very short, so it better be very bright to keep the solution errors down. And its spectrum has to be very well known.
But there are not many sources like this in the sky. Does it have to be close to our target source?
Well, fortunately not. Remember that bandpass is mostly instrumental. So basically the bandpass calibrator can be anywhere in the sky. It just needs to be visible over the horizon. Luckily for us.
Now what about the complex gain, G?
Well, we know that this changes in time, so we just have to look at the calibrator more frequently. So like this. But the solution interval now is just the whole frequency band at each scan.
Yeah, so the gain calibrator doesn't need to be as bright as the bandpass calibrator, but it doesn't need to be close to the target, because otherwise we'd be looking through a different atmosphere.
Right, and if we're only going to solve for gain phase, which often is all we need to do actually, then we don't even need to know the flux of the gain calibrator that well. So again, nature is quite kind to us here.
And now what's left?
Well, delay of course. We said that often delay is purely instrumental, so it varies slowly in time, kind of like the bandpass.
So can we just use the bandpass calibrator for delay calibration as well?
Exactly, often we do just that. If we know the delay is mostly instrumental, and if it's atmospheric, changing quickly.
Well, that sounds like gain. We can probably use the gain calibrator for it.
Indeed. And then we have all these scans in between to look at our target source.
Okay, so we've taken these observations. Is there a specific order in which we need to calibrate the effects?
Well, surely it makes sense to start with the worst one. And which do you think is the worst one?
Well, delay error definitely makes everything worse, doesn't it? Because it makes phases wind round and round in frequency, so you can't average. You can't do much until you've taken the delay out.
Right, so we solve for delay first. Now, which one would you do next, bandpass or gain?
Well, looking at this, bandpass here and here doesn't really care what the gain is doing in between. But the gain scans here They do care about the bandpass. So I think we need to solve for the bandpass next.
Right. And finally we solve for gain, and we transfer our solutions, and we live happily ever after, right?
But can we do even better?
Well, it turns out that we can do better thanks to a technique called self-calibration, or Selfcal, first invented by Cornwell and Wilkinson in 1981. We also call this second-generation calibration, or 2GC. Let's look at our Jones term again as a function of time. Let's say the true J, the one that we need to calibrate, behaves like this, the green line here.
And now we have our calibrator scans. In these we estimate our JCal. And now we transfer these to the target scans. This gives us JTransfer. And this is what we use to correct our target observations.
Now to simplify things, let's forget about the amplitudes for now. We already know from Fourier theory that phase is more important, right? So if we've done our calibration right, then the phase error, phi transfer minus phi true, is going to be within several degrees.
And sometimes that's good enough, and you can grab your image and do your science and not worry about anything else. But again, can we do better?
Well, let's consider the rhyme here again. So observed visibility is JP times the sky, XPQ here, times JQ conjugate, plus a noise term. Now, if we somehow knew the target sky a priori, we could just solve for J here directly, without any need for calibrators, right?
But if we knew the target sky already, we wouldn't even need a telescope. So why are we even observing if we already know about it?
That's right, we don't really know it. But can we get a reasonable estimate for it?
Well, yes, that's what calibration is for in the first place, right?
Right. So let's start by computing corrected visibilities. We do it here like this, we take the inverse of the J, and the J's we get from calibration. We get them from here.
Then we image the corrected visibilities via Fourier transform. That gives us our dirty image. Then we deconvolve using clean or some other method. And then we do an inverse Fourier transform, and this gives us the model visibilities, x sub qp. And that is our best guess for the target sky, for now at least.
And now here comes the trick. Now we can actually resolve for the J's using this X model and the observed visibilities we observed. And then we throw the solutions back into step 1, and then we rinse and repeat. And somehow, miraculously, this works. The J's improve and the images improve. This procedure is what's called self-calibration.
This sounds like an incredibly circular argument.
It is, and it feels incestuous. It has been compared to escaping quicksand by trying to pull yourself out by the hair. And yet, most of the time, it actually works.
But do we understand why it works? And more importantly, when it doesn't work?
Well, some of it is still a research topic, but we do understand some things. Firstly, it works because at any time and frequency point, for NA antennas, you get NA times NA minus 1 over 2 visibilities.
So we have many more equations than unknowns.
Yes, and also it works, as we sort of understand now, because the sky is actually pretty empty.
And presumably our initial guess, our initial first generation calibration with calibrator sources here, must be good enough.
And that, in a nutshell, was calibration.
That was a big nutshell.
Well, call it a Brazil nut. Anyway, in the next module, join our colleague Spey to put all of this into practice.